Okay, so the definition of a hyperbola, a set of points such that the difference of the distances from two fixed points is constant. The only difference between the hyperbola definition and ellipse is this word difference. So ellipse, it's sum. Hyperbola, it's difference. So with the sum, we showed you stretching that string all the way around. It's harder to show the difference, but you can see there's a minus sign down here in this equation. That's what's telling you this is a hyperbola instead of ellipse. Everything else about the equation is actually the same. So here are steps to follow, but I'm just going to show you the steps. The other difference with vocabulary in an ellipse, we talked about the major and minor axes. Major was always longer, major meaning bigger, major and minor. Now we're talking about transverse. So the transverse axis, and then there's a conjugate axis. They changed the name because the transverse is kind of like the major axis. It's more important, but it's not always the longer axis. So the transverse axis depends on which variable is coming in front of the minus sign, because we know that subtraction is not commutative. So it's not the same forwards and backwards like addition is. So with an ellipse, you just look for the bigger value in the denominator. But for hyperbola, you're going to look at what is coming in front of the minus sign. So see how in example 1, the x squared is coming first? That tells you that your transverse axis is horizontal. Does everyone have these notes 407 in your notebook? I'm on 407, not 407C, not the one I just gave you today. It's called 407 Hyperbola Parabola Overview. Does anyone not have that? You're all good of where we are? So in example 2, the y squared is coming first. It doesn't matter that 64 is a bigger number over here. The y squared is coming in front of the minus sign. So this is going to have a vertical transverse axis. So the rough sketch of what this hyperbola is going to look like is it's going to open horizontally versus in example 2, our final shape is going to open vertically. So it's going to be kind of an up and down parabola shape as opposed to side to side. So that's the first big thing to look for. What's this going to look like? Then your A, B, and C value are calculated in a similar way. So whatever comes first, that is A squared. So this is always A squared, and then this is B squared. So whatever comes first is more important, not necessarily larger. So in this hyperbola, A is just 4, because the square root of 16 is 4, and B is 5, because the square root of 25 is 5. So that may bother some of you. Oh, A is not the bigger one this time. A is more important because it comes in front of the minus sign. So our Pythagorean identity is different than an ellipse. So I don't want you to be confused and feel like I got to memorize all these formulas. I will put the Pythagorean identities for ellipse and hyperbola right on your performance task, so you don't have to memorize them. I'll also put the equation for eccentricity, C over A, because it's a lot of jumbled kind of alphabet soup. But in this case, because A is not always the bigger value, this actually has the C squared value as the bigger value. And when we draw the hyperbola, I'll show you why C squared is bigger. So you have to calculate C. So we're going to plug in 16 plus 25 for A squared and B squared. So that comes out to what? 41, 25, 35, 41. So C by itself is the square root of 41. I shouldn't use green because green is not a good color here. Okay. And the square root of 41, just so I know what it is what? 6 point something, 6.4. So when we're graphing our hyperbola, I'm going to show you what 6.4 is going to tell us. All right. I didn't even mention the center, but we know that the center is at 0, 0 because there's no H and K. So I'm going to put a dot at 0, 0 because that's the center of my hyperbola. So you start the same way you do an ellipse. In the x direction, right, x is horizontal, we're going to go 4 on each side and put our dot. 1, 2, 3, 4. and 1, 2, 3, 4, just like we did with an ellipse. I like to mark those as my vertices though. A hyperbola only has 2 vertices, and it's based on that transverse axis. So that I don't get confused, when I do my first set, I always put V next to them just so I don't forget. So now in the Y direction, I'm going to go 5, and I'm also going to put a dot. 1, 2, 3, 4, 5, but those are not considered vertices. 1, 2, 3, 4, 5. Those are just called endpoints of the conjugate axis. So instead of just drawing my ellipse, right, if this had been an ellipse, we would just circle it in. This is a hyperbola. So your next step is you're going to make a rectangular box around those 4 points. Doesn't have to be perfect. So the box is a framework of your hyperbola. And it's a framework for your asymptotes. So once you have your rectangular box, you're going to draw a diagonal line through the diagonal. So I'm drawing a diagonal that goes through the corner, the center, and the corner. So corner, center, corner. All that's the framework for your hyperbola. So your actual hyperbola, go back to where this vertex is. Here's your arm that's extending outward towards those asymptotes. So it goes through the vertex. I'm just doing it green to emphasize that the green part is the hyperbola. Everything else is just the framework. And that's it. You just graph the hyperbola. So a lot of what you know from ellipses helps you to graph hyperbolas. I think it's an easy transition to that equation. So I told you I would show you where the C value is. So it is also a focal point, and it's 6.4 units from the center on the transverse axis. So 1, 2, 3, 4, 5, 6.4. There's the focal point. 5, 6.4. There's the focal point. So the hyperbola opens around its focal points, or foci. And you can kind of see that the C value has to be the biggest this time, right? Because this is C, this is A, and this is D. So C is going to be the longest point this time. So in the Pythagorean identity, C squared is the biggest. And then it says asymptotes. So how would I write the equation of this line if I had to ask you the equation of this asymptote? The slope is up 1, 2, 3, 4, 5, and over 4. So this is just a line through the origin with a slope of 5/4. And this one is a line through the origin with a slope of -5/4. So y equals plus or minus 5/4 x. So reviewing kind of a linear equation, that would be the equation of those two asymptotes. The asymptotes are these dotted lines right here that go through the diagonal of the rectangle. So the equation of the asymptote, this one is y equals 5/4 x. This one is y equals -5/4 x because it has a y-intercept of 0. So I could write plus 0 over here if I wanted to. All right, so that's a hyperbola. Let's do one in the other direction this time. So let's go back to example 2. I still have a center at 0, 0, so I'm going to plot my center. And in the vertical direction this time, because y squared is coming first, I'm going to go up and down 6 and put my vertices. 1, 2, 3, 4, 5, 6. Vertex. 1, 2, 3, 4, 5, 6. Vertex. And I just put the V there for myself. So if you don't like putting the V's, you don't have to. But there's only 2 vertices, so you have to remember where they go. And then horizontally, I'm going to go 8. So from the center, I'm going to go over 8 and put a dot. This is a 10 by 10 grid, so if that helps you. Over 8, put a dot. That would have been my ellipse, right? So my ellipse, it's not an ellipse, it's a hyperbola. So we're going to kind of box in that rectangle to show the framework of our diagonals, which are our asymptotes. And then you can dot your asymptote in all the way across the box through the center in both directions. And then your last step is to draw your hyperbola. This is a really wide one because it's going through the vertex and then way out towards those asymptotes. So similar to ellipses, there's kind of an eccentricity. We're not going to talk about eccentricity for hyperbolas, but there's that wideness or steepness of a hyperbola too. And then I didn't calculate my C value, but I want to plot my foci. So a squared plus b squared, 36 plus 64 gives me 100, right? So this is a Pythagorean triple. So C would have to be 10. So my foci are located 10 units from my center, which is just going to be at the edge of your graph, because your hyperbola is opening around those foci. So I just wanted you to have seen a hyperbola, not do a whole lot with it, but at least know how to graph the equation. Ellipses and circles are more important for like seeing in pre-calculus, or calculus, I mean. Let's see, the equation of this asymptote, it goes to the origin, it goes up 1, 2, 3, 4, 5, 6 over 8, right? So 6/8 is a slope of 3/4 plus or minus 3/4 x. That would be the slope-intercept form of that asymptote, right? Up 3/4. It looks like I'm not going to get to parabolas today, but we'll do the back side of the hyperbolas. So depending on what tomorrow brings, I'll decide what you're going to have to do on your remote day. But I think I might just have you practice hyperbolas and we'll do parabolas together on Wednesday. That makes more sense. So let's see. Let's try some when the center is not at 0, 0. It's not going to change a whole lot. It just changes where the center is, and then you build your box the same way. So this time, whatever comes first tells you that the transverse axis is, this time is x, so horizontal. And the center, we already know how to find the center, is going to be left 2, up 1. So -2, 1 is the center. So I can go ahead and plot my center, left 2, up 1. And then my A value is the one that comes first. So my A value would just be 3. My B value comes second, so my B value is 7. So I'm going to go 3 in the horizontal direction with X. So 1, 2, 3. I'm going to label that my vertex. 1, 2, 3. I'm going to label that my vertex. And then I'm doing 7 up and down. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. That would have been my ellipse, but then now you're going to make your rectangle around all those 4 points the best you can. They don't have to be, it doesn't have to be a perfect rectangle. It's just to basically find the corners. So if you just want to find the corners, you do that too. Right? Because once you have the corner, you know that your asymptote, straight edge might have been good right there. Asymptote goes through those corners. I should be closer to my corner here. All right, so then once you've got your rectangle, your asymptotes, go back to where your vertex was and draw in your hyperbola. It should touch the vertex, but it should not go inside that rectangle, and it shouldn't cross your asymptote. So it should be kind of right out here. Don't go inside the rectangle, right? You don't touch the center. The center is just a guide point. And then our last step is calculating our C value. So a squared plus b squared would be 58, 9 plus 49. So what is the square root of 58? Comes out to 7.6. And your foci go on your transverse axis. So I'm going from the center, 1, 2, 3, 4, 5, 6, 7.6. There's your focus. 1, 2, 3, 4, 5, 6, 7.6. There's your focus. Asymptotes are a little bit trickier now that, see how I don't go exactly through a y-intercept with my asymptotes? So to me, point slope form is the easier form to use, which might blow your mind if you haven't taken Algebra 2 in a long time. Point slope form is y minus y1 equals mx minus x1. So if you know a point on the line x comma y and you know the slope, you can use point slope form. Then you don't need the y-intercept. So in this equation, both of these asymptotes go right through that center point. So I know a point that lies on the asymptotes themselves, and I know the slope. I went up 7 and over 3. So you can kind of steal the format from up here. Y minus y1 is going to be y minus 1 because I'm going through the point positive 1. So y minus 1 is plus or minus 7/3. And then I can kind of steal the format from over here. This x plus 2 is what shifted the center left 2. So x plus 2. So you're kind of stealing the center point from the original equation to do point slope form, and then you're using the slope just like you did on the front page. Yeah? Does it feel like it's really hard, or are you feeling like it kind of makes sense because you were familiar with ellipses? I'm hoping the ellipses helped make hyperbolas easier, even though you've never seen them. Okay, so last one. Yeah. Y minus y1 equals mx minus x1. You might get lucky and find the actual y-intercepts, but like I went up 7 over 3, so I have no idea what that y-intercept is without solving for it. So it's kind of the lazy man's equation for an asymptote where you don't have to find the y-intercept. You'd have to distribute the 7/3 times 2, so 14/3. And then you'd have to add 1, so 15/3. Oh, 15/3 is 5. Is this going through 5? Maybe that is 5 right there. Anyway. All right, I just wanted to show you this last one. So you've got to complete the square here. So let's just go through completing the square together. See how the 9y squared is kind of coming first and then the minus 4x squared? That's your cue to put the y squared stuff first. So 9y squared minus 36y minus 4x squared plus 8x equals positive 4. I moved the 4 to the other side. You have to factor out your 9 from this part. So 9y squared minus 4y, just like with ellipses. To complete the square, half of this squared would be positive 4 in the parentheses, which translates to positive 36. 9 times 4 is 36, so I'm going to add 36 to the other side. A little bit tricky, but you've got to factor out this negative 4. So when you factor out negative 4x squared, if you take out negative 4 over here, you're going to get negative 2x. So I see students mess up with that negative sign, but negative 4 times negative 2 gives you positive 8. So it should be x squared minus 2x plus 1, right? Because negative 1 squared is 1. So you're adding a negative 4 to the other side of the equation. Negative 4 times 1 is negative 4. So see how that comes out to a nice 36 on the other side? So this is 9y minus 2 squared minus 4x minus 1 squared equals 36. So let's just write our final equation and then we'll start with this, finishing this example next time. But let's at least write our final equation. So let's see, when I divide by 36 everywhere, I kind of ran out of room, sorry. What's my final equation going to be? It's going to be y minus 2 squared over 4, because 936, minus x minus 1 squared over 9 equals 1. So whether we're remote or together tomorrow, We'll start by finishing example 4, and then we didn't get to parabolas today. So I'll put the assignment, I'll either tell you in class or put it virtually, that you're going to be probably working on the 407C, just the hyperbola problems. And I'll tell you which bookwork problems to work on just hyperbolas. But if we're not here tomorrow, I said bookwork C is due Wednesday. If we're not here tomorrow, I'm going to make it due Thursday anyway. So just read the agenda if you have any questions. And the Google Meet for us would start at 9 a.m. And I'll just be on there, but your attendance is going to be in the Google form anyway. So even if you don't check in right at 9, just make sure you do the Google form for attendance. But at 9, if anyone's on there, we'll start by doing this example together. And if not, I'll put this example in the video so that you could do it on your own. Does that make sense? All right. So you don't have any official homework tonight, just whatever your assignment is tomorrow if you're home. And if not, then we'll be here tomorrow and we'll have bookwork C due Wednesday as long as we're here tomorrow. All righty? Thanks, guys.